All right. Well, hello everyone, and welcome back. If this is your first time, welcome to the workshop on using R for your laboratory work, data management, data analysis. So congratulations on getting through the first week. I think that was like probably the toughest week because it's so much was involved with um, sort of the nitty-gritty details of setting up your computer, and that's very frustrating. So today we're going to talk more about actually how to use R on your data. So I think that's going to be a lot more interesting, I think, hopefully for everyone. But just to recap on some of the issues that came up over the last week, and also just remind you always, if you've got problems or things aren't working for you, feel free to put them in the issues section of the GitHub repository for the course, and that is linked from the course website, as you probably know. One of the issues that came up was, basically all the issues that came up were with connecting your computer to GitHub, and understandably so. It's a sort of a challenging thing to do. Number one, I would say, don't let that be a barrier for you using R for your work. It's useful, it's helpful. I do it. But it's not necessary. So you can feel free to disregard the Git stuff and just leave out any of the Git commands that show up on the scripts, and you by and large will be fine. The things to point out that people had some issues with were, number one, make sure, mostly having to do with basically this box down here on Git commands. So of course you have to obviously join GitHub first, and you can do that at that link. But people need to make sure that they have, quote unquote, introduced themselves to Git using these commands here. This is basically what you're going to fill in with your, you're going to fill this in with your login here. So this would be, say, your today. This would be your login, and this would be like your email that you use for GitHub when you register your account. And that way, the computer and the website are going to be able to talk to each other. This thing here you have to run. That will get you your personal access token. It's like your password, and then you have to run that to set it inside in the internal mechanism of your computer. And once you've done that, then you're basically done with this whole block forever, and you should never need to change that for your computer. The other thing that came up was using Internet Explorer. If you have that set as your default browser, that's going to cause some errors. So you'll have to change that if that's the case. Okay, so let's get started talking about the subject matter for today. And I want to start, before we even get to R, I want to start with arranging your data. And when people say data science, it's sort of a broad term, but there actually is a science to it, and it's the science of enhancing reproducibility, minimizing errors, and basically letting the computer work efficiently with what you have put into it. And I will show you how I used to store all of my data, and probably most of you store your data at one point or still do in this sort of format. And so let's say, and this is like an example of a format that is not useful for a computer. Okay, so you have an experiment that you did, and maybe you're counting some colonies, or you're counting some spots on an image, and you have a control group and you have an experimental group. Okay, and you put all of your control values in this column here, and you put all of your experimental values in this column here, and then you'll use Excel to calculate the mean and the standard deviation, and then do a t-test. And this works, and you can actually get by really totally fine like that. The issues are when it comes to I would say reproducibility primarily. Because now the way you've got it here, you've got your data, which is this part, and you've got your analysis, which is this part living in the same document. And it's very easy to say, go back and say, I want to do a new analysis. I want to do a new calculation on these data for whatever reason, and then to accidentally open up the wrong file, or to open up the file and then, maybe like drag and drop accidentally a new value. So you change your data when you don't really mean to be changing your data. All you want to do is do a different analysis on it. And so the principle of separating your data from your code is, and your analysis is an important one. And so the first thing that we would do in order to make this a better, a more, let's say, reproducible and a more computationally friendly sort of situation is we would get rid of the things that are not data from our data. So we'll get rid of stuff like that. And what you want to do actually is you want to transform your data set into a flat file where each row is an observation, okay? And each column is a feature or an attribute of that observation. So let me just very simply show you how to do this. So what we can do is we can instead take these values here, and I'll just copy them, and I will put them down here, okay? And what we'll do is we'll make a new column here, and we'll say this is experimental group, okay? And for all of these values, the experimental group is going to be control, okay? So that's how I would do it like that. And this column will be, say, number of spots, for example, spots counted on our image, okay? And so now what we can do is we can simply take this set of values there, paste it down there, and these are our experimental. So this is one of the annoying things that Excel does that will cause you errors, is it automatically completes these things. So you just have to be careful with that sort of thing. And so now we can fix it like this. Okay, so that took like 30 seconds to do. It was very easy, but it is another process that you have to do on your data, which means that you can make a mistake at it. So you want to try and avoid that. And the way you avoid that is by, when you're logging in your data to begin with, log it in like that. So make every row an observation and every column of an attribute of that observation. And you can put any number of attributes in here. So let's say this was the date that the experiment was done, okay? And you can say, the person that did the experiment, all sorts of things. And so then your data is now not in sort of columns that are mismatched, but rather in a large flat file, okay? So that's point number one. Point number two is saving it in a format, and this is not totally necessary. R can read in Excel files, but the less complicated, the better. And so I prefer to save all of my files as CSV files, which are, basically comma-separated values, simple text files. And this will save space. It will make you, it will make your analysis more error resistant because there's less complicated things to get messed up. So usually I would just save this not as an Excel file, but you want to save it as a as a CSV. So as you can save it here and just change this to this guy here, comma separated values. Okay. All right. So that's just an example of how you can make your life easier by starting off with your data in a way that is computationally efficient. Okay. All right. So let's move into R. Okay. And just as a reminder, I think folks have probably, started your own projects, and so if you have your own project going, you're going to be able to, basically take this script and run it for yourself or run something similar to it. All these commands are here on the notes page, okay, in these note pages, and you can, just copy and paste these into a script. You will also be able to go to the GitHub site for the course and get this from the workshop project. And yeah, so you'll be able to get it from here, from the R section of the workshop project. So this will get pushed up to there. And if you want to clone it, if you know how to do that, or fork it to your own repository, some people have already done that. That's totally fine. But you can also, just click on the file, and then you can go to raw, and that will just give you something that you can easily copy and paste. So that's very easy to do if you're interested in doing that. Okay, so what I've done here is what I will do actually is I'm just going to restart our session just to show you exactly how this should run. Okay, and so when you sort of sit down to work in using a project in this way, you're always going to start with your dependencies file. Okay, this is going to load the libraries, going to load the packages, the commands, the functions that you're going to be using for your analysis. And so this is already set up because we did it last week, and so we'll source that, and so that's run, and now all of the commands are ready to go. All right, I'm just going to pause 1 second here. I'm going to tell the guy to stop vacuuming up here. Excuse me. Can you stop doing the vacuuming? I'm in the middle of a class right now. I can't do it. You come back in like an hour? 1 hour. 1 hour. Thanks. Okay, sorry about that. Okay, so we've run the dependencies, so now all of our functions are working. The next thing we're going to do is run the configurations, and this is going to set up preferences and other attributes for our analysis. That's a very easy thing to do, but we always want to get in the habit of running those 2 scripts first. Okay, and now we're here in the week 2 script, and so like I said, you'll be able to copy this at any point after today. Okay, so the first thing you want to do is you have your data on your computer somewhere, and you're going to read that into R, and it's going to basically, turn it from a text file into a sort of a digital representation of that inside the R world. Now, the command that we use to do that is this command here, read CSV. Okay, there are variations on this that you can use. You can use, as I've got here, this is like a website. But normally what you do is point that to a actual file on your computer or your network drive somewhere. So if I run that, what it does, it grabs that data and it reads it in, and it's turned it into a what's called a tibble. Okay, so a tibble is like a data table. Now, what are these data here? These data are example data that basically ship with R and allow you to practice, certain manipulations of data or plotting or whatever you like. I've done some modifications to this. I added a column just to make it a little bit more, just to give us something else to talk about here. And I've basically deposited it here on my website. So that's all this is. You'll read in your own data, and you'll have some values, and you'll have some attributes. And yeah, so that's how you do it. Now, what we've done here is we've just simply read it into R, and R has spit it back out into the console down here. All right, and that's when you don't assign anything, that's all it's going to do. So let's look at what it's got here. It's got columns. Okay, so it's a table of 150 rows and 6 columns. Column 1 is observation, and then there's some measurements about these flowers. Okay, and these are like species of iris. Okay, iris is a flower, and it's got different measurements here in millimeters, I guess. Okay, so that's all good. So what are some things about this? Well, under here you can see the column name, but under the column name is this thing here. It says DBL. That stands for double. These are all doubles, double, and that stands for that's a CHR. That stands for a character. A double is basically like a number, like a numeric value. Okay, so doesn't matter why they call it double, but it's a number. Okay, character is obviously like a letter. It can be any character. It can be a numeric character, like a 1 or a 2, but treated as a character rather than as a numeric value. We have a question here in the Q&A. So how are tibbles different from a data frame? Well, good question. They are very similar to data frame. They have some additional features which make them, a little bit more efficient to use, and some better features than a regular data frame. Tibble is part of the tidyverse packages, which I'm highly recommending that everyone use for their analyses. And they integrate well with the style of commands that we're going to use towards the end of the lecture today, using the dplyr commands. So good question. You can consider it for all intents and purposes the same thing as a data frame. So, all right. So yeah, so back to this. We've got some columns here, and this thing under here is called the type. Okay, so we can have one, which is a number. It's also can be a character, can be some other things, but the way R treats it is called the data type. Okay, and you can think of this similar to like a categorical variable or a numeric variable in sort of your basic statistics sense of things. And so it's really important when you're importing your data, you always want to check and make sure that the type is inferred correctly. So R will look at some values and will say, oh, I think this is a character, or I think this is a number, and it will automatically treat it as such. And you want to check and make sure that's correct. And I can tell you, and I made this sort of ambiguous on purpose, is that observation here is being treated as a numeric value. And that's actually not quite right, because an observation, it's just like the first number of an observation that we made. This happened to be the first observation. This was the second observation. So it's not really a quantitative value. It's more of like an ordinal number. So it's actually more of what we would call a factor rather than a numeric value. Okay, and R will often do it right, but often make mistakes too. So, but what we can do is we can actually instruct R to interpret that column not as a double, but as a factor. Okay, so and that's what this command here does. So this is the same line, except I've added this information here on the end. It tells us to treat the first column as a factor, the next 4 as doubles or numeric. Remember, double is the same thing as a numeric, and the last one is a character. So if I run now this command here, this has fixed it. Okay, so now it's a factor rather than a numeric value. Okay, good. So hopefully that's pretty clear. So now what we've done is we basically, read these data and then sort of regurgitated them back out into the console, which is maybe not the most useful thing to do. Usually what we'll want to do is to store these in memory so that we can use the data to do some additional manipulations or transformations or calculations, however you want to think of it. So the way to do that is called what we call assignment. Okay, and so assignment is like a basic function of all computer programming languages, and the way it's done in R is with this leftward pointing arrow. Okay, there are some other ways you can do it, other symbols that you can use, which are not as good in my opinion. So I think you should always use this leftward pointing arrow. And so what will happen is the computer will perform this command here, and it will store this information as this variable here. And this is going to show up here in our global environment. Currently, our global environment is empty because we haven't stored any values in it. But what we can do is we run this command, it will store this tibble here as this thing here called demo data. Okay, so I've run it, and so now it's shown up here in my global environment as basically a data frame. I can make this a grid, and I'll tell it's a tibble, and it's this size, and it has 150 rows and 6 columns. All right, so that's a very useful way, thing to do. Now, when I've run it, it hasn't shown up here in the console, and that's because I told R not to print it to the console. I told it to save it in the global environment. So all I have to do is I can run it, and that will spit it back out into the console like so. Okay. So I want to talk a little bit more about what is a data frame or what is a tibble. So data frames and tibbles, like I said, are pretty much very similar and can be used for the most part interchangeably. Fundamentally, they are lists of vectors, okay? And a vector is the fundamental unit of data, the fundamental data structure in R, okay? And a vector is simply a collection of one or more values of the same type, okay? So we talked about types. Type is numeric or a character or a factor, etc. So a vector has to be all of the same type. It can be anything from 1 to a very large number of those values, okay? And so let me demonstrate what it looks like when we run this. So we make a vector using this command here. C stands for combine, and you're going to put all the values into parentheses like that. Okay, and so we've made a vector and we've asked R to spit it back out into the console here, and you can see that these are, when there's no quotes around them, that means they're numbers. Okay, but we can make a character vector as well. So, and they look like that. Very easy. The quotes mean that those are characters and not number values. Of course, A is not a number, so it's automatically treated as a character. Okay, we can, just to demonstrate the point that 1 is also a character, or can be also a character, we can show it here. Okay, so now we have 1 being treated as a character. It's in quotes. That means it's not a number as far as R is concerned. Okay. Let's say you tried to, or you forgot to put the quotes around 1. R will recognize that as being a problem, and it will convert it from a number 1 into a character 1 here. So just to reiterate, a vector has to be all the same type of value. Okay. All right. So let's, like I said, a data frame or a tibble are lists or a collection, more or less, of vectors. So if we look at demo data, again, we can run it. You can see that each one of these is, in essence, a vector. It's an observation as a vector, sepal length as a vector, et cetera, et cetera, et cetera. And these are all bound together into a larger data structure. And so what we can do is we can, actually, so sorry, before we go on, question, why wouldn't R recognize why wouldn't R recognize this as a list or a data frame instead of a vector? Well, because we've used this C here that's basically the command that creates a vector, okay? So here, so C creates a vector, okay? Now list creates a list. And there's other ways to create tibbles and data frames, but the best way is to just read it in as a CSV. So that's a good question. All right, so so what we're doing here is we're extracting values, okay? And the sort of syntax that R uses to extract a value is these double square brackets. And what you're going to do is, if you wanted to extract the second column of demo data, you would put it inside these double square brackets, and you can run that. Now head, you don't need to worry about that, just gives you like the first 5 values. But if I run this, you get 5.1, 4.9, 4.7. And so that's the first 5 values of the second column here. Okay, so that's extracting. You've taken basically a collection of vectors and you've extracted the second vector from that. Okay, so that's, we're going to get into something different in a little bit called subsetting, which, so that's a little bit confusing because subsetting is going to use a very similar notation. But let's just sort of stick with extraction for a second. So you don't have to just use the column position. You can actually use the column name. And the way you do that is you just put that column name in quotes inside the double square brackets. Okay, so now if I run that, that will give you this setosa here. Okay, and so if I go back up here, so it's extracted the first 5 values of the species column from our demo data. Okay, so that's another way to extract. Now, by far the most common and most, I think, useful way to extract data is to use the $sign. Okay, now the $sign is nice because R is going to help you out when you try to do this, and so you'll just put in demo data, and if you put in a $sign, it will automatically understand that you're trying to extract a vector out of that data frame. Okay, and so then you can just simply type in whatever one you want, like for example sepal length, and if you run that, it will give you the whole set of values as a large numeric vector. Okay, so extraction takes a complicated object and removes part of it as a simpler object. So you've changed the form of what you're working with. You've gone from a table or a tibble to a vector. All right. So I think, in your daily working life, you're almost always going to be using the $sign to extract. So that's the most important one to remember. So I'll just type that here. Most important. All right, good. So now subset is a little bit different. And I think, we're going to, towards the end, a little bit later, we're going to talk about better ways to subset than using this type of notation or this syntax. As you go through, you might encounter situations where you have to use this, which is why I'm telling you this. But and the reason that it's confusing is because it's very similar to extraction in terms of the syntax, but it does a very different thing. And so subsetting will give you just a smaller version of what you started with. That's the best way to understand it. So if you start with a tibble and you do a subset, you're going to get a smaller tibble. That's it. So what this will do is it will, this particular command, it will subset to retain only the second and third columns of the demo data. Okay. Now this is always, you have to remember this. The first thing is a row. So that will take all of the rows and then only the second and third columns. Okay, so I'll show you that. So now we've got a smaller version of the original tibble, but with only the 2 columns that we told it to collect. Okay. We can also subset by row, and like I said, it's always, you have to remember this. It's row comma column. So you'll run this, and that will give you the first 2 rows of your data frame or your tibble. Okay. You can use, the column names, as they are. If you prefer to do that, usually that's a better way to go when you're trying to be explicit. And so that will subset your return a tibble with only the species and observation columns. Okay. All right. So yeah. So what we want to do now is we want to generate a list, and we should have some code in here to generate a list. And it looks like I forgot to copy it over. So let me find that. Yeah. Sorry. So I have to find our list here. Put this in here. Go back here. My apologies. I'll get the list. Okay. So let's talk about lists for a second. So lists are, and I don't want to be confusing, okay? A list is a more general term. So we talked about vectors. Vectors have to be all the same type. Now, a list does not have to be all the same type. A list can be like a collection of any object. Any valid R object can be in a list. And this is really going to be really useful, you know, as you start to do more complicated things, where you, you know, are going to try and say, return a table and maybe a plot and maybe like, some other more complicated data structure altogether, out of a function. And so you're going to have to know what lists are. Just remember that lists are a general form, a more generalized version of a vector. Okay, so the way you do that is you make a list like that. Okay, and if I run demo list, it looks a little bit different. And so the way it prints out here, the first element is 1, the second element is a B, and the third element is this word Charlie. Okay, so and each element is a single vector in this case of length 1, and another vector of length 1, another vector of length 1. So what this really is a list of vectors of length 1. Okay, so that's how that looks. And you can do a lot of things that are very similar to what we've already shown with the data frames and with the vectors. The syntax is going to be a little bit different looking, but it's good to know. We can put names on lists, and this is useful if you want to say, provide some documentation or explanation of what these values are. And so if I do that, then if I run demo list again, we can say that the first object, the first element of the list is a number, and that number is 1, a letter, B, a name, Charlie. Okay, so named lists are actually very useful to have to keep yourself organized. We can also extract and subset lists. Okay, so it's a very similar syntax to what we were doing with the data frames or the tibbles. You use the $ to extract things like so. Okay, so you can subset the list using the single square bracket. You can subset it by name, using the name that you've provided if you provided names for your list. Okay. All right, cool. Next, go back to my notes here. So the next thing that we want to do is we want to talk about operations. Now, operations are, basically, they might be functions, or they might be like simple mathematical procedures like adding and subtracting, or a logical test. Is one thing greater than another? Is one thing equal to another? These sorts of things. There are lots of good references for you. So if you go to this link here, this is from the course website. If you can go there, that does a quick list of all the different operations that you can use. All right, so that's a good reference for you. And so let's talk a little bit about what it means to do operations or mathematical or arithmetic in R. Okay. So like I said, you're using a vector, and a vector is a collection of numbers. And so we can run a function on that collection of numbers to return a value. And like the easiest one I can think of is mean. All right. So if we look at this value on the inside here, that's a collection of numbers, that's a vector, and we can get the mean of that by running that command there. Okay. And so that is a very fast operation. You always want to try and use the built-in functions that operate on vectors it doesn't matter for a vector of 150 or 130 values, but when you get to 130,000 values, it might show, it would take a long time if you didn't use the vectorized operations. So things like mean and standard deviation, these are all sort of fundamental functions in the base R package that operate very quickly on a very large collection of numbers. So you want to use those as often as you can, okay? But we can add two vectors together like this, okay? So this is a numeric vector here, all right? 1 and 2, there's two values there, and we can add these two, and that's a 2 and 3. And if we add them together, we get a new vector, which is the first value here plus the first value here, and then the second value here plus the second value here. So we get 3 and 5. Okay, so that's how vectors are added. Now, you may also want to add vectors of unequal length. All right, so as I mentioned, 1 is a vector, okay? It's a vector of length 1, and you can add that to a vector of length 3, as shown here. And what happens is R recognizes what you're trying to do, and it recycles this vector, the shorter vector, and adds it to each of the values here. So if I run this command, I get 2, 3, and 4, because I've added 1 to 1, 1 to 2, 1 to 3, and I get 2, 3, and 4. So that's called vector recycling, okay? So let's say you're in a situation, and usually this would be something that you don't want to do, but R will let you know that this is a problem. Let's say you try and add vectors of unequal length. Okay, so now you're going to add 1 and 2 to 1, 2, and 3. This is not going to come out equally because this is not a a multiple. This is not a multiple of that. All right, so if I run that, what happens? Well, it returns a value, but it says that the longer object is not a multiple of the shorter object, so that gives you a warning and says you probably don't want to be doing that. But it has taken this value, added it to that, so I get 2. 2 plus 2 is 4, and then it's tried to recycle this 1 here, so it's added this 1 back to this 3, and so I've gotten 4. So that's a little bit of an unorthodox, not good behavior. So you want to try to avoid situations like that. So that's like addition and basically any other mathematical operation you can think of, you can use like that. Here are some logical tests, all right, greater than, less than, equal to. These return what are called Boolean values, all right? So I'll just type this in here. Logical tests. So that's a true or a false. Okay, so 1 is greater than 0, that's a true. That's a true. So 1 does not equal 3, that's also true. 2 is less than or equal to 1, that's not true. Okay, so these are things that you're going to find useful, as you start to do more complicated things. I know it seems pretty basic right now, but that's the syntax for using operations on vectors. Okay. All right, so the last thing I want to talk about today is I want to go through a better, in my view, syntax or methodology or style of coding. You can definitely get by using the base functions, which is what we've talked about up until now. But there's advantages to using the tidyverse style of coding and using pipes. And the advantages are that it's much easier for the human to read and interpret and sort of add on to, debug if there's something that's not working, than the base R functions are. So I would highly recommend that you use the tidyverse style of coding, and most of what we're going to talk about today is from one particular package called dplyr. And dplyr is basically just about manipulating data, rearranging, reordering, and doing calculations, which is what you're going to spend a lot of time doing. Okay. All right. So let me just show you one resource that you will probably find valuable. Okay. And this is the dplyr cheat sheet, and you just get this by Googling dplyr cheat sheet. But that's how you spell that, dplyr. Okay, and this will give you, a pretty good understanding if you forget the small details about how you're doing for how you do the subsetting or the filtering or the joining or mutating, these sorts of things. So use this. I still use this pretty frequently if I forget how to do something. All right, so the way we start here is we have our data, and remember our data is a tibble, and the tibble is the best format for basically using this style of coding. This symbol here is called a pipe, okay? And this pipe is going to take this data and it's going to feed it into the next line, all right? And what it does is it takes that data and makes it and inserts it as the first argument to this particular function here, okay? So if I were to do this, it gives me the option to identify some data as my first argument to this function. But I don't want to have to type that every time, and the pipe automatically fills that in. So the pipe is going to take this demo data and put it right in there. So all I have to do is I can just get rid of this, and I can tell the computer what I want it to do with the data. All right. And the way this is structured, it's going to pass that data into here. This line will do something with our data, and then this next pipe will pass it to the next function. That function will do something with our data and pass it to the next function. And so as long as you stay within a set of functions that operate in this way, that take your data as the first argument and pass it on in a different form, but in whatever form to another function, then you can put in really a unlimited more or less number of these commands to manipulate your data. And the nice way to do this is it's a very logical flow. So the first thing, we're going to start with our data, then we're going to do this mutate thing, which I'll tell you about, then we're going to group it, and then we're going to summarize it. So it does those things in that order. And if you're trying to figure something out and you want to remove that, all you have to do is you can comment it out, or you can delete that line. And so it's a very user-friendly way of manipulating data from one form to another. So what do these terms mean? Mutate is a function, okay? And so functions usually will take in data, they do something to that data, and they return data, all right? And what mutate does is it takes in a tibble and will do a calculation, and you have to just provide that calculation for it, and then it will add the result of that calculation as a new column in your tibble, all right? And so that's what mutate does. And you can see that here on the cheat sheet. If we go back here, mutate makes a new column, all right? So there's your data. Mutate will add a new column on there. So here, what we're going to do is we're going to make a new column called sepal length width, and that is going to equal the length plus the width value. All right, so if I run sepal data, we have this. This is our data that we're working with. It's going to add that value to that value and make a new column here. Okay, so I can run just that much just to show you what it's got. We have a new column, which is this value plus this value. So 5.1 plus 3.5 is 8.6. Okay, so that's like the formula that we provided is right here, and it's returned the new tibble. Excellent. So that's good, but we still have now a lot of values and want to sort of like get a summary of that data so we can eventually compare some groups. Okay, so what we want to do is very naturally arranged. We have a column here called species, and if I just run this, I can show you that, well, I'll just run this. It's going to group it by species. And so I run this much. It says that there are now 3 species groups that we've created. So that's new. That wasn't there before. Now we have 3 groups. And so what R is doing is it's holding it in its brain and says, okay, now all the rows that have species of a certain value, those are in a group. It hasn't done anything to our data yet, but it's like got this in its mind. This will usually be followed by a function called summarize. And what summarize will do is it will perform another calculation based on those groups that you've provided. And let me show you here the difference between summarize and mutate. So mutate takes a formula and makes a new column. Summarize takes a formula and takes the whole vector by group and returns a single value. Okay, so you have a large table with a lot of observations going to a smaller table by group. Okay, it's called a summary function. So if I run this whole thing, it will make this new value for each observation. It will group it, and then it will summarize it by group, and it will calculate the mean of this new value. Okay, so there we go. So here's the species. There's 3 species, Setosa, versicolor, and virginica, and it's calculated the mean value for each of those groups. All right, and so just to sort of demonstrate what we've done, compared to working in Excel, is we haven't touched the data. The data is the same. It's still on our computer. It's still on the website. And we've done all of our grouping and our mathematical calculations here in code so that we can, not interact, not mess up the data. And we know where the data came from. We can always go back to it. And if we want to change our analyses, we can always do that. So that's very simply the most important, take-home point for today. Okay. Now there's a lot of other things that we can do, this is what you're going to have to, I think, learn a lot of this just by doing with your own data. So let's say you want to get rid of an observation, or rid of a column. You use this select command and you put a minus sign in there. So we'll go from demo data. Okay, we want to get rid of observation. We'll get rid of it. Okay, so now that's gone. Let's say we wanted to select certain columns. We can use this. Okay, you want to filter, and so this is analogous to a subsetting operation, but I think it's much more clear. So now we start with the demo data, and we're going to filter it such that the species is equal to this Setosa. Okay, so I run that. We've now gone from 130 or 150 observations down to 50, and they're all just the Setosa values. Okay, we can say select more than one thing to filter for. We use this operator here called in. That's sort of a group set function, and so what that will do is it will retain any observations where species is either Setosa or versicolor. Okay, so I can run that, and you can run this on your own, but basically there's 100 values. There's 50 Setosa and 50 of the versicolor. All right. Another thing that is going to come up from time to time is the concept of long data versus wide data. And so what we have here is, I think, a pretty typical way to think about your experiment. Maybe you have like some sort of an animal that you've done some measurements on, and you've done a lot of different measurements, and here are all the measurements, and each one is a column. Well, this is actually useful for us humans to think about. In some cases, it might be more convenient for a computer to have that in a long form. And what this will do, what this function pivot longer does, very simply, is it takes all these values and puts them in a single column, and then it will add a new column that more or less describes what that value is. Okay, so let me just demonstrate. So I can make a new thing here called long data, and if I run long data, we now have a new column called name, which was previously the column name. Okay, and the value, which was previously the value for that column. And so now we have a 600 by 4 tibble. Okay, and so that's pivoting. It's called pivot longer. There's a little bit of have to do a little trial and error to get it to do what you want. One important feature is that the columns that you want to pivot should all be of the same type. Otherwise, that will cause an error or cause some weird behaviors. So you'll notice that these are all double or numeric. So we've only selected the double or numeric columns to pivot when we did that. okay? Because in the end, they're going to end up in the same column, and every column is a vector, and every vector has to be of the same type. So you should always make them of the same type. If your data ends up like this, you can pivot it back using pivot wider. And so that brings it back just the inverse operation of what we just had just done. Okay, so the last last thing that I want to talk about today, there's a lot more that we could go through, and I think once you've gotten through this much, you'll sort of have a good foundation to start exploring and practicing. But I want to talk about joins for a minute because these are super useful, and use them all the time. And you can have some errors or some weird behaviors, so you just want to know about what they're doing. The basic idea for a join is it's similar to something like a VLOOKUP sort of thing that you might do in Excel. But basically, you're going to take two tables that should share a column name with similar values or the same values, ideally. And you're going to want to, and they can be in any order, which is often why you're doing a join rather than just mashing the two things together without checking. But what you're going to do, what the computer does is it will take every value from, and I'll just show you here, from the first, you're going to want to join, let's say, these two tables together. And you're going to then create a new table that has all the values sort of stuck together. Okay, and you can see here ABC, ABD. This new table has ABCD. Okay, now there's some missing values down here, but that's okay. So in any event, so that's how you're going to do a join. The principles are you need to have a column to join by. You should ideally only have one column that is similar between the two tables that you're going to join. And these columns have to have similar values, otherwise there's nothing to join. Okay, so let me show you. So we're going to make two smaller tables. So we're going to take this, make a table of the sepal data, which you should recognize how we made that. And so this is just the sepal data, sepal length, sepal width, and we can take the petal data. Okay, if I run that. And so we are now in a perfect position to join these back together. Obviously, this is just for demonstration, and probably you would have done some other calculations or created these two tables in different ways. But we have two tables. They have a common column here called species. The values are of the same type, so they're both characters. They have similar and, in fact, identical values to them, these three species names, okay? And we don't have any other columns that are the same, okay? Now you can match or you can join by multiple columns. It just gets to be a little bit ambiguous sometimes, and generally you don't need to. So you always want to, if you can, pick one column that you're going to join by. In this case, we're going to, we don't even have to tell R to do anything in particular. It will automatically recognize that you're trying to join by species, and it will just do it. So if I now run left join sepal data and the petal data, it will join them back together like so. Okay, so we've now taken two tables which are different. They could have been in any order. There could have been missing values, and we've joined them back together. Okay, so that's joining. All right, so we are almost at the end of our time today. So I'm going to look at a couple of questions we'll try and answer here. How would we use the pivot function? So I don't know. Just to sort of, maybe, I don't know if this was answered already, but you have to select the columns that you want to pivot. All right, so if we start with demo data, oops, fix that. Data. We start with demo data. You're going to pipe that into pivot longer, okay? And you're going to tell it the columns that you want to make longer, okay? The rest of this stuff is going to be just duplicated, as additional attributes or additional descriptors for your values. And the stuff that's in these columns here, I can't really highlight it, but this stuff here, these numbers, those will turn into like a value column. The column names will turn into a name column. All right. And so the way you identify the columns that you want to pivot is just like this: cols equal, and then a vector of those column names. Okay. So if we run that, you can see it's just going to convert those. Everything that was a column now gets the column names get put into this column called name here, and the values go here. And the types are okay. So the type is still a double, which means that it's still numeric value that we can use. Okay, hopefully that answered that. So what happens if you add two different types of vectors, say a character and a number, where you get an error, or R will force one type into another? That's a good question. So let's try it. So we can do 1 plus A. That's an error. Okay, so that will show up. Under some circumstances, it might try to coerce a value, but yeah, that's usually a sign that you're not doing something right. And another question: what is the difference between the pipes, the two different pipes? Exactly. So good question. There are some subtle differences between like these two different versions of the pipe, and I can briefly explain by saying that this is the new version. This is an old version. This guy here is added to sort of like the base R distribution. So when you install R, you don't have to install anything else. It comes with this functionality, which is good, because then in order to use this, you have to add in a package. You have to load a package, basically. And that's not a problem. I mean, usually like, this automatically gets loaded when you use the tidyverse packages, and I'm suggesting that you always basically use those. Yeah, so fundamentally you can, for the most part, use either. There's some more subtle differences, like in terms of the syntax. This one tends to be a little bit faster, but that's a very subtle difference as well. So I think as far as I'm concerned, you can mostly use either one. I've switched to using this one, because I try to use things from the base package, when I can, as long as they're not clearly inferior to other packages. And I think this is fine. So that's a good question. Okay, I'm just going to make sure I got most of the other questions here. Yeah, so it looks like we answered everything. All right, cool. Let me just make sure I hit the last bit here. Yeah, so I just wanted to, make sure you guys are trying this as we work along, over the next week. Try running the code here. This is going to be put up into the GitHub site. So actually, I don't have it here, but you'll find it. Yeah, again, it will be here. If you can go, this is under the data science curriculum. Actually, no, that's not right. It'll be under the workshop project. This is also public. You should be able to find it. Workshop project. It'll be in the R folder, and you can just download it or copy it however you want to do it. I also want you to try to use data from your own experiments, reformat if you have to, but put it into a CSV, read it into R, do some data manipulations that you may have already done in Excel so you can compare the results. And then as sort of like extra credit, try doing some basic statistical tests. You can do t-test or Wilcox test. This is just, simple stuff that we always do. And here the hint is, in order to do those, you want to feed in numeric vectors for your groups into those functions. And by now you should know what numeric vectors are. Okay, great. All right, it's 11 o'clock. Thanks for paying attention, guys. Remember to put any questions you have in the issues section, and good luck. Thanks a lot.